Hey, listeners. You might have heard of the Netherlands, a flat country in Europe known for its windmills and tulips, tall people, and cycling culture. Well, it also happens to be a thriving hub for ALD, with a plethora of researchers and companies spread across the country, like ASML, the creators of the first commercial EUV lithography instrument. Over the next episodes of ALD Stories, I'm going to chat with a couple academics from the Netherlands about their ALD activities. This month, we're really happy to host Professor Erwin Kessels, renowned professor of applied physics at Eindhoven University of Technology. Erwin, an Eindhoven graduate himself, is known for his work in plasma-enhanced ALD, or PALD, and its applications. As an alternative way to perform ALD, PEALD uses a plasma as part of the deposition process to enhance surface chemistry, tune materials properties, and enable the deposition of new materials and shifted temperature windows. Erwin and I talk about some of the basics of PEALD and differences from thermal ALD, uses in the semiconductor and solar industries, and wrap up with his fantastic outreach activities, including the Atomic Limits blog. If you've been enjoying the ALD Stories podcast and this content, please like this video and subscribe to the Bennick channel. We would also love to hear your feedback, so please comment with who you'd like to see on the podcast or what topics you'd like to see discussed. So thanks again to Professor Kessels for his time and participation on the program. And with that, please grab your tea or coffee and enjoy episode 8 of the ALD Stories podcast.
Welcome to ALD Stories, a series of conversations where we share the untold stories of atomic layer deposition and the people behind the technology. This podcast is brought to you by Bennick, the home of ALD.
Thank you again for joining me. I think today I'd like to have a conversation on plasma ALD and some of the work you've been doing. You are a renowned person in plasma ALD here, so I think as a resident expert in the world, it would be great to have this conversation with you and have a number of things that we could chat about, whether it's just basics of plasma ALD or some of the more specific work that you've been going on. But it might also be nice to touch on some of your other activities, like the Atomic Limits database and the ALD Academy as well. And when I did my ALD work with Steve George, I really didn't ever touch a plasma. We had them in the lab, but none of my work involved it. If there may be some other ALD people out in the world that are a little less familiar maybe with PEALD. And so maybe to start, we can give a little bit of context and you can go through what are the key differences between plasma enhanced ALD and our typical thermal ALD.
Okay, so, well, in principle, I always say that plasma ALD is very similar to thermal ALD, apart from, of course, that there is one step in the ALD cycle, which involves in a plasma. And that, of course, leads to quite some major differences in terms of the hardware, because you have to strike a plasma. And well, the plasma plasmas are actually pretty complicated. They are very complex because I always say they have like a will of their own. They do whatever they want. So you can plasmas are very nonlinear systems. So if you vary a parameter, that the plasma will change, but it's very hard to predict how the plasma will change. But the nice thing of plasmas in ALD is that they are relatively fairly simple plasmas. So you use an oxygen plasma or hydrogen plasma or a nitrogen plasma, for example, and they are fairly simple. What they basically do is they provide radicals and other reactive species to the surface. And these radicals, for example, hydrogen atoms or nitrogen atoms or oxygen atoms, they can contribute to chemistry. The fact that they are very reactive, that is, of course, very helpful for the plasma itself, for the ALD process itself. But there are also other species, electrons, ions, etc., and they can also contribute to the chemistry. So, as I said, the cycle is very similar. You do precursor dosing, purging, plasma exposure, and then purging, and then during the plasma you have the chemistry enhanced by the plasma species. But for a lot of people, as I said, plasmas are very complicated, and you really need to know what you're doing. But other than that, I think the cycle is pretty similar.
So I mean, you mentioned that despite the using very simple plasmas, things like nitrogen or hydrogen, that they tend to be complex. Like, what are the knobs typically that people can turn with plasmas that you do have control over? And with I know there are a few that I'm sure you will get into, and having more of these kind of parameters that you can work around. Do you find that there is more control over the type of film that you can produce versus just using normal thermal ALD?
Yeah. Well, that's maybe to start with the latter. I think there is many more things possible. So if you use water or ammonia, I think you're somewhat limited, of course, at what you can do. But with a plasma, you can change the plasma properties quite a bit, and that can also have an influence on the properties, on the film properties, of course. The knobs, so with plasma, you flow a gas, you flow a hydrogen gas, for example, you strike the plasma, and two important knobs are the gas flow, the pressure. The pressure is, I think, probably even the most important one, and the plasma power, and that basically determines for large extent the plasma properties and what happens at the surface. Of course, you also very much depending on the hardware, because you have different types of plasmas. You have capacitively coupled plasmas, you have inductively coupled plasmas, microwave sources, ECR sources, etc. So that also has an influence. But I think the pressure and the type of plasma, they are probably very important parameters, basically, that you can that mostly determine the plasma properties, I would say. And then there are kind of variations that you can do. You can vary the plasma gas. You can add mixtures. So you can use, if you want to do a nitride, you can sometimes work with a metal organic amide precursor and use hydrogen gas. But you can also use nitrogen gas, or you can use hydrogen-nitrogen gas, and there you can make you can have different properties of the film. So, for example, a very classical example that we worked on in like more than 10 years ago was tantalum nitride, where we could vary between the cubic tantalum nitride when we used just a hydrogen plasma, and the dielectric tantalum 3 and 5 and using that was with a nitrogen hydrogen plasma. So that's some variation that you can do, and actually the good thing at that stage was that we could get the cubic tantalum nitride, the conductive form, by plasma. And with thermal ALD, that was very hard. People would usually get the dielectric material, and people were interested in the conductive material. A plasma contains electrons, ions, and neutral reactive species. What we have been doing is also look into the role of ions. So ions are in the plasma, and they, depending a little bit on the pressure, or actually depending on the pressure, they also get accelerated to the surface, and they can get quite high ion energy. Well, that's something that we also started to study how that would work for plasma ALD, and in earlier 2010s. We started to also investigate the role of ions and also the role of the ion energy, and actually control the ion energy by applying an additional bias voltage to the substrate. And there we found out that actually by controlling the ion energy, we could actually also control the film properties. So we had some very classical examples where we were able to tune the crystallinity of the films from amorphous, basically, to a crystalline film. For example, for titanium dioxide or for hafnium oxide, we could make crystalline materials even at low temperatures by controlling this ion energy and actually having pretty high ion energies involved. So that's a knob to turn. For example, the only thing that you do is you drive up the voltage that you apply to the substrate holder where your wafer is on, and then you can control the ion energy. Well, some materials improve under ion energy, and some materials actually deteriorated under ion energy because they don't like these high ion energies. So that's another, very important aspect of ions of plasmas, that you can control the ion energy and also can control the material properties. If you don't want the ions, then you work at higher pressure and you suppress the ion energy. If you do want to have the ions, you can increase the ion energy, and then you can benefit from their influence and control the material properties.
Are there trade-offs with when you are trying to control this ion energy, if you want them or if you don't want them? Does that then affect the plasma and end up with some kind of negative effects for films, or does it not affect things as much other than this amorphous and crystallinity that you mentioned?
In many cases that the material improves up to a certain ion energy, but after that, if you even go to higher ion energies, then you can get damage, because that's what people are typically kind of afraid of with plasmas, that you have a lot of ion damage. And that is that can be you can have ion damage, but that we found out that typically is only at high ion energies, very high energies. So the plasma itself will not change. The ion energies, the ions are only accelerated to the very narrow sheet region that is very close to the substrate. So the plasma is hardly affected by itself.
Now, one thing I am very familiar with plasmas is that they are typically directional. Their line of sight, which I believe is the same for both etching and for deposition. When you have these ions and you can kind of control the ion energy, are there opportunities for biasing in other places on a substrate to maybe get ions into harder to reach places that might depart from the traditional directionality of the plasma?
Well, yeah, that's a very good question, actually. So these ions, if you accelerate them by increasing their energy, they have a directional component. So as I said, this is also what you use in anisotropic plasma etching. Mm-hmm. Then you used to use these ions to etch your trenches or your vias. So the ions, they have this directional component, and it's a little bit hard to have them also to reach also difficult to reach places by these ions. So if you want to do a very conformal deposition with ions, that's going to be hard because the ions will be directional. So that is something that is complicated. It's for lower aspect ratios, it's fine if you want to have an aspect ratio of maybe 5 or something. For trench, we have shown that ions still hit the sidewalls to some extent. And for many applications in industry, this is sufficient. Many applications in industry don't work with extremely high aspect ratios. So then the ion energy and ion energy control can certainly also be helpful. But if you go to very high aspect ratios, then that's not the case anymore, and that is then you would not be able to do that anymore. Alternatively, and this is something that we have been also exploring, and we have written some papers about this, is that if you use this ion energy, you can also use this for topographically selective deposition. So then you want to deposit maybe one material at only horizontal surfaces and not on vertical surfaces, or you want to have some anisotropy using these ions. There are also some other possibilities that you can exploit. So yeah, the answer is, if you want to deposit very conformal with the ions, that's going to be hard on very high aspect ratios. But it's actually also providing some opportunities now for topographically selective deposition. And there are some opportunities in industry, actually, for that. So that's something that you could exploit.
Could you maybe go a little bit, expand a little more on the industry applications for this area selectivity with the ions?
Yeah, there's one. There's one application in NAND, 3D NAND memory, where you would like to deposit only on horizontal surfaces and not on vertical surfaces, or you would like to at least not have very good quality material on the vertical surfaces. And that's actually where you deposit some silicon nitride at the staircase for the contacting with the tungsten. And what I understand, our companies are using actually the directionality of the ions to create good silicon nitride on horizontal surfaces and poor quality silicon nitride, or maybe no silicon nitride, but probably poor silicon nitride on vertical surfaces, to add a little bit of silicon nitride on the staircase, which helps for contacting these staircase with the tungsten in the end. So there is a process that is being exploited quite big time, I would say, in 3D NAND. And that's one example. It's maybe not the best example. It's it's a little bit of work around it, how they do it right now, but I think there might be more applications, because in the field of ALD, we see a lot of interest now in area selective deposition, also something that we work on. But now the next step might also be topographically selective deposition, and there I think ions could play a role.
And is this only possible with the directionality of the ions, or if you have no ions in the plasma, will you also be able to do this type of topographically selective deposition?
Well, it's hard to rule anything out, but I think it would be difficult, because this directionality it's so clear. So it's such a well-studied aspect of plasma. So I mean, that's the same thing with plasma etching. It's very difficult to do anisotropic etching by other methods than with plasmas with ions. Yeah, so there are sometimes some tricks, but that's all plasma etching. All this anisotropic etching is basically plasma etching nowadays in the semiconductor industry. So I don't want to rule it out, but I think the plasmas would be very helpful for doing this.
Great. I'd like to go maybe into a little bit of mechanistic things, particularly I guess this is a little more basic on plasma ALD, but we're not using the typical precursors that we usually use, or the typical like oxidizers like water or something like this. So the mechanisms I imagine for the surface chemistry are much different for plasma ALD than it is for thermal. Could you walk through what the typical mechanisms are, and how these radicals and this enhanced surface chemistry works in PEA?
Mm-hmm. Yeah, sure. Well, we did quite some investigations of the surface chemistry during plasma enhanced ALD. And of course, it depends on the material, whether you deposit an oxide, a nitride, or a 2D material. But it's not always that different. For example, for oxides, the classic case of aluminum oxide, we actually showed that the surface chemistry is actually very similar for almost all processes, all steps of the ALD cycle, apart from the plasma step. So where in thermal ALD you have water interacting with the CH3 groups, if you use TMA, then with the plasma you have oxygen atoms reacting with the CH3 groups. And in the plasma case, you will have not ligand exchange, and you don't eliminate CH4, but with plasmas you would eliminate. You basically have combustion-like reactions, and you remove and you create CO2 and water as main reaction products. So then the surface chemistry is basically combustion. But the striking similarity is that in both cases, and this was a surprise for us, in both cases you end up with a hydroxyl terminated surface. So, okay, the surface reactions are different, you make different reaction products in the gas phase, but the surface groups for aluminum oxide, TMA oxygen plasma, are the same as for the TMA water case. So that is the classic case of aluminum oxide, and I think this holds for more oxides, that the surface chemistry is somewhat different because you have combustion of the surface ligands, but that maybe the end result, or how the surface is terminated, is the same. Now, for nitrides and for other materials, it's sometimes somewhat different, I would say. But then it's also somewhat harder to compare. For example, some nitrides are difficult to make with thermal ALD, and then like silicon nitride. So then surface chemistry is, you cannot really compare. So it very much depends on the material that you deposit, of course, but the bottom line is that it's not that different sometimes. Huh?
I'm curious on what you see as probably the most advantageous part of plasma ALD versus thermal, and where in industry that has had the biggest impact so far.
Yeah, so well, that's also a very good point, and well, I think plasma ALD will exist next to thermal ALD in industry. If thermal ALD works well, and then there is no need to go to plasma ALD, because plasma ALD will always have a little bit more sophisticated hardware. But there are some reasons in industry to use plasma ALD. One example would be if there is no process, or not a good process, for the material that you want to make. So I was talking about silicon nitride, but also silicon oxide. These are materials that are very difficult to make with thermal ALD. Okay, silicon oxide you can use with ozone, but silicon nitride, you don't have that equivalent. So if you want to do silicon nitride, you have to maybe rely on plasma ALD. Another example is another key aspect of plasma ALD is that you have these surface reactions by reactor species from the plasma. And so that means that there is more reactivity coming from the gas phase, coming from the plasma. And that means that you can work at lower temperatures typically, because you don't have to drive the chemistry completely by this temperature. And that's another example where you want to make a material and you are very much limited, maybe in thermal budget. Then it might be a good idea to use plasmas, because maybe the thermal process only runs at 200 degrees C and you can allow for 50 degrees C. So that's a clear example. Well, there are quite a few applications where this is the case, where you have very sensitive materials. Then you might want to use a plasma. Sometimes you can use ozone if you want to do an oxide, but also ozone when you get to low temperatures, for example, to room temperature. It sometimes the chemistry is not, maybe you can make a film, but it's not high quality, or it's actually very slow. So we demonstrate several room temperature plasma ALD processes that give very good material quality, even if it's at room temperature. So that would be another reason to use plasmas. And then there is another aspect that can be interesting and important is, for example, productivity. Very important in the semiconductor industry, of course, for some applications. And if you go to low temperatures, for example, you can make good quality or reasonable quality aluminum oxide, but the process is going to be very long at low temperatures because you need to purge the water, etc. So then plasmazole can also be helpful because you can have much shorter cycle times and still have a good throughput. Now, if you look at the applications of plasma ALD in the semiconductor industry, there is one big one, and that is, for example, silicon oxide. Silicon oxide for patterning, for example, where they do this spatial defined double.
The double patterning.
Yeah, there's spatial defined double patterning, right? yeah, so that is yeah, actually you couldn't come up the name anymore. And space defined quadrupole patterning. That's where they use plasmas a lot for depositing the ALD material that is going to be, you know, that will be part of the mask in the end. So and that is, if you do silicon oxide, there are several reasons to use the plasma. Silicon oxide is hard with thermal ALD. Okay, you can use ozone, but plasma ALD would be is typically better. The other thing is that you need to work at low temperatures. Certainly if you deposit directly on the photoresist. Yeah, and the third one is that the productivity is very important, and they typically have this high volume manufacturing tools, which, you know, they have to have a lot of throughput, and then the plasma is also helpful. So silicon oxide in industry, I think it's mostly deposited by plasma ALD, and it's one of the big applications of ALD nowadays, right? So in terms of tools that are installed and of wafer runs, because this lithography, you know, you need to do this several times, and with these most advanced layouts nowadays, the technology nodes, you need several lithography steps, and there you have to, the wafers goes through several of these several line double patterning steps or quadruple patterning steps. That's silicon oxide. Another application we recently found out is that silicon oxide is often also used as to fill up vias. And they are, and actually also to protect sidewalls of high aspect ratio features in NAND. And there, what turns out is that silicon oxide ALD by plasmas is still very conformal. And we did a study on this. We published this 2 years ago, I think. The student just graduated, where we demonstrated that plasma ALD can still be conformal up to aspect ratios of, you know, I think we found out 800 aspect ratio of 800. So
wow.
This is another thing that maybe is good to mention, because often people think that plasma ALD is not conformal. Well, if the plasma ALD process is driven mostly by the radicals, then for some materials, plasma ALD can be extremely conformal. And a very nice example is silicon oxide and also titanium dioxide can be very conformal even with plasma ALD, and you can quote up to aspect ratios up to 800 if you work with a sufficiently long plasma exposure time.
And so you see good step coverage, everything with this.
It is possible. It is possible. As I said, you know, you need to understand your process. You need to know what you're doing with the plasma, but it's certainly possible, and people are using this in industry. So this filling of vias, for example, by plasma ALD silicon oxide, that is being used now in industry.
I've noticed that you have been doing a lot of work in outside of just the semiconductor industry, particularly in surface passivation. I know that is also important in some applications in the semiconductor industry, particularly with new gate materials like germanium and so forth. But you also do a lot in solar cell fabrication. Is that right? Yes,
that's correct. Yeah, well, yeah, I've been working on solar cells next to this, you know, the semi applications already for many years, and there is actually quite a lot of overlap in materials that are being used. You know, they both use silicon wafers typically, and but there are also many differences, I would say. One thing that we worked on heavily, and we're still involved in this, but this is now also transferred to industry, is actually the surface passivation of silicon solar cells. If you take a silicon solar cell, then you want to absorb the light in the silicon, and then you want to carry away the electrons and so the electrons and holes to the two different terminals of the solar cell. And you want to collect the electrons, and you want to collect the holes. But what typically happens at surfaces is that you can have defect states where electrons and holes can recombine. And then you lose your electron hole pair, and that's that's bad because you would like to collect them. You want to harvest all the electrons on all the holes. So surface passivation is a method where you apply a thin film on the surface of a silicon wafer to reduce this recombination of electrons and holes at the surface. At some point there was actually interest in passivating the backside of a solar cell. And what we found out in our research when we were working on aluminum oxide is that aluminum oxide can passivate surfaces very well and actually reduce this recombination. This was due to two reasons. One is that there was always, when you deposit aluminum oxide, there was always a silicon oxide interlayer. So that makes the silicon oxide interlayer is, the silicon oxide interface is very good. This is what we use always, of course, in also in semiconductor industry. But we also found out that the aluminum oxide would have a high fixed charge density, and that is in the aluminum oxide, and that would shield the electrons from the surface. And this was something that was not good for semiconductor industry because people don't want to have dielectrics with charge typically. But for solar cells, it was actually wonderful because that would reduce the recombination of electrons and holes. So we found it out, and we found that the aluminum oxide would lead to very good surface passivation by thermal ALD and by plasma ALD, and we did a lot of studies on this. And then finally, it got actually accepted by industry to be applied in industrial solar cells when people were making the move from the traditional aluminum backside surface, that was the aluminum backside contact, to the so-called PERC cells. And PERC is basically a passivated rear. And that was a transition that happened in industry around 2012, 2014, maybe, that it was really adopted. And then people started to use aluminum oxide for passivating the surfaces of these, the backside surfaces of solar cells. And if you buy a solar cell right now, just a good solar cell panel, I would say it's very likely that you have a PERC solar cell, as a panel with PERC solar cells, in which the backside of the surface is passivated by aluminum oxide. And nowadays, it's very likely that this was done by an ALD process. Initially, it was also a lot of plasma-enhanced chemical vapor deposition, but now there have been high productivity tools launched such that you can also do ALD at high productivity. And now I think most of the solar cells have an aluminum oxide surface passivation at the back, which is made by ALD. And interesting is, I think, that the number of wafers that are run in the solar cell industry is much larger than in the semiconductor industry, because you need so much more wafers and to make panels, that that this is a big market in that sense, in terms of the number of wafers that you deposit for ALD, right? Because it's one of our major ALD applications nowadays.
Did you find that there was difference or kind of an advantage to using plasma in any of these processes for passivation, or were the properties of the passivating layer different based on thermal and plasma ALD?
Yeah, there were actually for crystalline silicon, we found that for plasma ALD, the passivation was typically better than for thermal ALD. But the point is that what do you need in the end? So it turned out that thermal ALD was good enough. So plasma ALD could get better passivation, but that was not the limiting factor anymore. And thermal ALD can do well enough. And then if you look for solar cells, as I was explaining, you need to deposit so many wafers. So then you need to think about how the productivity tools. So that actually motivated people to work with batch ALD, and they use batch furnaces at relatively low temperature, by the way, 200 degrees C, so it's not a high temperature furnace, where they maybe load 500 wafers, and that would be impossible by plasma ALD. So that's why they have resorted to thermal ALD. It's good enough. With plasma ALD, you can maybe make it slightly better, but it's not a limiting factor. And then other things count, you know, money, the cost, but also the productivity, of course, that is of course connected to that. So the passivation layers that I was describing, they're all done by batch processes or by spatial ALD processes. But I think the batch is winning from the productivity point of view and simplicity point of view at the moment.
I saw one of your, I presume is your student at the AVS 67, who was talking a bit about the germanium passivation.
Yeah, so that's I mean, the passivation holds for many applications, not only for silicon and for silicon solar cells. It has also applications in actually also semiconductor applications, or in photonic applications, for example, or other you know, kind of niche applications. So the germanium work is mostly for photonics, where people try to make silicon-based light sources, for example, and then you want to work with maybe tiny lasers, where you also need passivation, and this kind of thing. So that's why we're working on that. But of course, it's also now with the gate-all-around structures. Then also you have to control the surface states. Maybe the passivation that we do is not always applicable, because we sometimes like this high fixed charge density, and that's not always good for logic applications, for example. But well, it very much depends on what you want to do.
I did want to touch on your other activities outside of research, because I think they're really interesting. And for me, as somebody who really appreciates outreach, I'd love to have them plugged on this platform. So I was hoping you could maybe talk about how you started, or the importance of the ALD Academy and the Atomic Limits blog.
Yeah, so yeah, that was like, these are a little bit, you know, side things that I do, and they're somewhat kind of more hobby-like. But well, the Atomic Limits blog is something that you know, things are changing all the time. How people, you know, publish the results and you know, have outreach. So I think it's like 5 years ago that we thought maybe we should also do something with a blog, and there are some very interesting ALD blogs. Well, one particular, Boulder Engineering, that you know, and we all love that, you know, and that's very nice, by Jonas Sundquist, and we like that. We said, well, you know, there might be something that we can do in addition to that, somewhat different, you know, where we want to have original content, and we want to report about our research, the kind of things that we do, or about trends that we see, that we spot, and all kind of other things, but from like an original point of view, so original content. So we talked about this topographically selective deposition. You know, if you want to publish a paper on this, it will take maybe a year to do that, and you have to have good results. But if you have an idea, or you pick up something is interesting in industry, then it's much easier to write a blog about it. It's not like, you know, it's not peer reviewed. It's not like from that standard, but I think it can be very helpful to, you know, to share with our colleagues, and to you know, make sure that this is maybe a direction that other people may also pick up. So that's one of the reasons why we put up this blog. One thing that we also did, and you were referring to this already, is also this ALD database. So I think you all remember this paper of Rika Purina, where she added in 2005 a Journal of Applied Physics, where she added all the ALD processes that were reported at that time. So at some point we decided, okay, maybe we can turn this paper, and also other papers, review papers, and just the papers all in the literature, we can turn that into a database on the internet. And so that was actually the ALD database. So where people can look up whether a material has been deposited and what kind of processes have been reported, and even have a direct link to the paper. And also people can contribute to this database. So if somebody makes a new material or has a new process, you can add it. We will review it so that we don't get any nonsense in there. And then we add it to the database. So it's a crowdsourcing. And with this, I think we have a very nice resource where people can look up the materials that have been deposited by ALD. And it's a community thing, so we it's for free, but we also we really rely on people that add the processes.
Well, if anybody is listening right now doing ALD, ALE who don't know about the atomic limits ALD and ALE databases, get on there now if you're doing something new, and please please add.
Yes, please do so. So that's on the atomic limits block as well. There is also an image library where we try to collect high quality images. You know, I think images are very important. So that's something that's on there, and there's some other interesting content, and we run this with a group of people. But in principle, we're happy for everybody to, to get involved, or if there was something that somebody wants to get posted. Of course, we have our kind of rules, our standards, but it's not an Eindhoven University thing in principle. Of course, we run it mostly, but it's I think it's a very nice resource. In addition to one of the Bold Engineering one, which is much more, which is faster, which is more about news. This is a little bit more about trends and more things, a little bit slower in that sense, but more and this kind of stuff.
It's a really nice platform for people to contribute, and do you find it to be maybe a little more like academically driven than Jonas's?
Yes,
he's so
for
plugged
sure,
into the industry. I saw that you had been teaching a course a little bit differently, and it was a plasma processing course, if I remember correctly, and you were teaching it more as a in-depth from an industry perspective. Would you mind talking about that a little bit?
Sure. No, I'm happy to do so. So we teach a course which is called plasma processing, but that's basically a course about semiconductor manufacturing. So it's about deposition, etching, and patterning, lithography. And we teach people about plasma etching and ALD and all of these kind of things. So it's very close to our actual research, and it's not necessary. It's not only semiconductor industry, but it's heavily semiconductor industry related. Also with a company like ASML here, one of our neighbors, where there was a lot of lithography. They are leading in lithography, and a lot of our students go there, so they might want to know a little bit more about semiconductor processing before they go there. So we have regular lectures to explain that, but we also have kind of assignments. This is what we call, and this is a popular term right now in education, and that's challenge-based learning. So you don't say, okay, these are the lectures, you have to learn this. You give them a challenge, and then they, with the knowledge that they have gained, and they should address that challenge and work on it. So what we asked them to do is actually look into some manufacturing steps of very advanced technologies. So we say, okay, 3D NAND, how do you make a 3D NAND device? So maybe take this device of Micron or Samsung, and there is like sometimes there is some reverse engineering paper or reverse engineering website, Tech Insights, for example, and I would say, okay, dig into this and describe all these processes, or several of these processes that are involved, and make a report on this. So, or like the new iPhone, has like this logic chip. So with FinFETs, and how does this work? How is it being made? So then the students have to go really into that, and then they look at all the TEM images and this kind of things, and they have to dig out how this device is being made, or at least some of these steps. We try to narrow it down somewhat, but then they work on maybe a device that is launched, 2 months ago, and then they try to understand that. So that's what we call challenge-based learning.
That sounds nice. It gives it can be really easy to feel disconnected from the actual real world when you're in class or you're in academia. I feel even sometimes when you're doing the research, and I imagine to gain a more kind of tangible perspective on this broad, huge world that you're entering into has to be insanely valuable to these students.
Yeah. It's typically considered as an eye opener, and I think that's really nice. And people get sometimes extremely excited about how technology works, and much more from the excitement that you would get from a textbook. So I think that's what we want to achieve.
Yeah, that's great. I love that approach so much. Well, okay, Erwin, I have to thank you so much for taking the time to be with me today and to chat with me about all of your work and Plasma ALD and your other outreach activities. I really can't thank you enough. I really appreciate it.
Thank you very much. I was really a pleasure to do so, and thank you for asking me for doing this.
Yeah, of course. Is there any last thoughts or things on the horizon you'd like to shout out before we wrap up for today?
No, not really. I would say just follow our blog, and see our LinkedIn post, and that will take you to the blog. And then if you want to do that, then you can stay updated with our interest and our work. That would be my advice.
Perfect. Well, everybody listening, you heard it here today. Please take Professor Kessels' advice and follow the blog, follow the work, and tune in for the next episode of ALD Stories.
You're listening to ALD Stories with Benek, the home of ALD. To stay tuned for new episodes, make sure to follow us on Spotify, Google Podcasts, or Apple Podcasts. We hope you enjoyed today's show. Talk to you in the next one.